If you are watching this video, that means you have already tried learning DSA from big names, you name it. But let's be real, most of us still forgot those concepts after a week or a month. So after watching this video, I bet you won't need to watch any other tutorial because I have covered almost everything. You can check the code in my GitHub profile and don't forget to join the Telegram channel for more updates. So let's get into our video. Hello everyone, so in the previous videos, we have already learned how to detect cyclic and director graphs using DFS, BFS, and in the last video we have also seen that how to do it in director graph using DFS. So in this video we'll do it with BFS. So before going to the problem, let's see today's insight. Never ever learn solutions of problems by doing reverse engineering. Learn from people who actually tell you why we are doing what we are doing. Because most of the people who are present out there who is teaching DSA, when they come to detection of cycle using BFS and a directed graph, they'll directly teach you about topological sort. Can bet you that there is not even a single video which will teach you actual intuition and why we are doing that. So let's get into today's problem. And I have previously said that DFS is like front end and BFS is like back end. You understand it today, why did I say this? So let's take this example one where there is a cycle present and this is the adjacency list and we'll do a BFS traversal. So let's take a queue. We'll start with node 1 and we'll mark this node 1 as visited. Then we pop node 1 and push node 2 into the queue and we'll mark this 2 as visited. We pop node 2 and we'll push node 3 and we'll mark this node 3 as visited. And then we pop node 3 and we push node 4. And when we pop node 4 and we try to travel across the neighbors, then we see only node 1 here. And we see node 1 is visited. So we'll treat this as our approach 1. Let's try same for this example 2 where there is no cycle. So we'll do a BFS. We'll take a queue and we'll start with node 1. We'll mark this node 1 as visited and we'll pop node 1 and we'll push node 2 and we'll mark this node 2 as visited and then we pop node 2 and we push node 3 and then we mark this 3 as visited. Then we pop node 3 and we don't have any other nodes which are connected to node 3. So the BFS call is completed. So then we'll move to node 2 and we see that node 2 is already visited and we move to node 3 and we also see that node 3 also visited. We'll start another BFS call starting with node 4. We mark this 4 as visited and we pop node 4. You see for 4 we have all the 2 nodes which are connected to this 4. All these are visited. But we have ended up into the same situation as in the previous 3 cases. Let's observe something and let's try to observe is there any difference between these 2 cases then. So if we try to observe the differences, here we have only one BFS call and here we have 2 BFS calls. That's it, right? Even in the previous video we have done the same. So here we can see 2 BFS calls, but this is not the case because even you might have another node 5 which is connected to 4 and you will have another BFS call here. But this case doesn't work in the both cases. Even in the case where the cycle present, we'll get 2 cases. So we'll get back to our previous approach. We can see that this 1 and 3 belongs to this BFS call and this 4 belongs to this BFS call. So as in the previous case we have done, here also we'll try to maintain another visitor vector 2. And we see is there anything that we can figure out from that. So let's try to maintain visitor vector 2 and we'll try run for this again. So we'll start with node 1. So push node 1 into the queue and we mark this 1 as visited and then we pop node 1 and whenever we are popping it, we will unmark it. And then for fun, we have node 2. So we'll push node 2, we'll mark this as visited and then we'll mark this as visited and then we pop node 2. So we are popping it right, we'll unmark this. Then again from 2, we'll push node 3 and we'll mark this 3 as visited here and we'll mark it as visited here. And when we are popping 3, we'll unmark it and we'll see for 3 we don't have any connected nodes here. This BFS call is completed. We'll try to do another BFS call and we'll start with node 4. When we push 4 into the queue, we'll mark it as visited here and pop this and we'll mark this as unvisited. And we try to travel here. We see that 1 and 3 are already visited, right? And they're not visited in this vector 1 and 3. So we'll say that, yeah, even the previous case we have done the same and we have figured out right. So we'll say there is no cycle here. But let's see, is this working with the example where there is cycle present? We'll see whether this intuition is working for that or not. So let's try run for this with the same approach. So we'll start with node 1. So let's push 1 into the queue and we'll mark it as visited. And then we pop it, we'll unmark this and we push node 2 into the queue, we'll mark it as visited. And then we pop node 2, we'll unmark it. And then we push node 3, we'll mark this as visited. And then when we pop 3, we'll unmark it and we push node 4, we'll mark it as visited, visited. And then we pop node 4 and we'll unmark this, and we see only one node which is connected to node 4, and we see that node 1 is not visited in visited vector 2. So even in the example 2 where there is no cycle, but we need this node 1 to be visited in order for this graph to be cyclic, right? So we are failing with this intuition, because in BFS we had that tree structure where we are able to access that recursive nodes. But in this case, BFS does it by layer. So that's the case we are not unable to solve this by using the same thing. So that's the reason why we are unable to distinguish between cyclic and non-cyclic. This approach too will fail. So we cannot do like this. So we'll try to see is there any other approach. So in the first approach, we tried with the adjacency list. Is there anything unusual in this adjacency list? And we got that all the nodes are listed. And then we got the same case in both cyclic and non-cyclic. And then we failed this approach, and then we tried to figure out something using this BFS calls. And then we figured out something like we had two BFS calls here and we have one BFS call here. Even with that approach, we have failed here. So we have tried with this and we have tried with this, and the only thing that is left here is the graph. If we have to do anything, we have to go with this approach, like using this graph as our main intuition. So let's try to figure out something using this graph representations. So let's take these two representations of the graph. There is no cycle and here there is a cycle. So what can we do using this representation of graphs? So when we have graph representations, what we can do, what differences that we can find from two graphs? Either we can differentiate by directed or undirected, or we can find in degrees or out degrees, and we can find number of components, all these things, right? So we already have this better on that, right? So let's see with in degree and out degree. Let's try to write in degree and out degree of each one. So for 1, we have in degree 1 and out degree 1. And for 2, we have in degree 1, out degree 1. And for 3, 1, 1. And for 4, 1, 1. So if we write for this graph, we have 1, 1. Now 1, 1. Here we have 2 in degree but 0 out degree. And here we have 0 in degree but 2 out degree. Is there anything that we can observe now? So we can observe here the in degree of 4 is 0 and here it is 1. We have written out in degrees of each node. So we can observe that for node 4 we have in degree 1 here and in degree 4 here. Can we directly say that if we can find in degree of all the nodes as greater than 0, then we'll say there is a cycle present there. And if it is anything, if we cannot find anything like that, then we'll rightly say there is no cycle. How far is this truth? Let's try to see. So we can observe here is, if there is a cycle present in a graph, then for sure there should be in degree and out degree then in degree of each node should be 1 for sure, right? I think this approach will work here, I think. But let's see, is there any contradiction cases for this? But what if we have node 5 here, which is connected to node 4, where in degree of this node 5 is 0. So this case is merging up with this case. He said that if we have all the integers greater than 0, only then we said there is a cycle. But here the integer is 0, but even though we have a cycle here. So this intuition fails here. And also we did not use BFS in this approach, right? So let's try to combine this in degree approach with the BFS. So the only unusual thing that we can observe here is for node 4, we have in degree as 0. So we'll try to start BFS with node 4 because we have all these nodes as same with in degree 1. There is something fishy with this node 4. So we start with node 4. We'll push node 4 into the queue and we'll mark this 4 as we start. And then for 4, we have node 1 and 3. push node 4 into the queue and we'll mark this 4 as visited. And for 4, we have neighbors as 1 and 3. But the integrity of 1 and 3 is greater than 0. So, do we directly push this into the queue 1 and 3? There is something missing up here. Like, we have pushed 4 into the queue with integrity as 0, and here if we are pushing it 1 and 3 again, then we are going to mess it up. So, what we can do is, here we have degree of 1 as 1. So, we'll try to decrease it. We'll mark it as 0. And here we got integrity as 0, then we can easily now push it. If you are decreasing the integrity of one neighbor, then we have to do it for all the neighbors, right? So, we'll also do it for neighbor 3, and we'll decrease to node 1, and we'll decrease to 1. Then we mark this 1 as visited, and we'll decrease this integrity to 0. And for fun, we have node 2, and we see node 2 having integrity as 1. So, we'll decrease to 0, and we have got our required case, which is integrity 0. We have popped it and we have pushed 2 into the queue, and we'll mark this as visited and we'll decrease its integrity. And then we pop node 2, and for node 2 we have node 3. And for 3 we see integrity is 1. So we'll decrease it to 0 and we'll push it into the queue. And we will mark this integrity as 0 and we'll mark it as visited. And then we pop node 3, and for node 3 we don't have any connected nodes. So our BFS call is completed and we are able to reach all the nodes. So let's try to do for this example 1. So, but we don't have any node such that integrity is 0, right? So, but you might say, what if we add this node 5? So if we add this node 5 here, the integrity of node 5 will be 0, but the integrity of node 4 will become 2, right? So we'll push node 5 into the queue, and then we'll mark this as visited, and then we'll pop node 5, and for 5 we have 4 as neighbor. So 4 will decrease it to 1, and we see, is it 0? No, right? And will not push it. So here we have ended up doing BFS traversal only for node 5 here. Did not visit all this 1, 2, 3, 4 nodes. So I think we have got the difference between these two, right? We have observed the difference between these two. That's the thing. That's how we solve this problem. See, do you find this as complicated at any case? We are able to distinguish between cycle and non-cycle using integrate. So that's how it is done. And so we did not directly jump into this by directly taking integers and decreasing that. We have figured it out step by step why we are doing what we are doing. First, we started with example 1 and we tried to do using adjacency list, and then we figured out it's not working. That's how you think and approach the problem. And so I said this is BFS as backend, right? Now, did you understand it now? Like, what does it actually mean by a cycle? Like, so if a graph has a cycle, you cannot visit all the nodes by doing BFS traversal by linking it to integrity, right? And we have observed something like the integrity of each node in this graph. If it is a cycle, then the integrity of each node should be greater than 0. But it is not same as in the case where there is no cycle. This is actually what a cycle means. It is not a visitor, not parent and visited. This is not all the things that we have to remember. What it actually means for a cycle, if somebody in an interview or somewhere, if we ask you about what is a cycle, and you have to tell this, the integrity of each element will be greater than 0 and you cannot reach all the nodes by doing BFS by linking it to integrity. This is the actual backend of the whole thing. You need to understand this. If you can understand this, then you can easily figure it out for any other thing. In the last 3 videos, we have done not parent and visited, and then we have used visited vector 2. All these are way of approaching the problems. But the actual backend for the cycle, it is this. So I think you have got the clarity of why did I call DFS as front end and DFS as back end. So let's try to write short code for this. So we'll call function with, it doesn't say list and number of nodes. And then what we have done first. So first we have figured out integrity vector. Traverse the graph and find the integrity vector. And next step, what we have done, we have pushed all the nodes where its integrity is 0. In order for us to push all the nodes which in integrity 0, we need to traverse through the integrity vector. If we find integrity of any index as 0, then we directly push it into the queue. And we'll also declare a variable count and we'll increase that. So we'll initialize the count variable here. Because in the case where there is no cycle, we have visited all the nodes. That's the only difference where we can differentiate between the cycle and non-cyclic, saying that if we are able to visit all the nodes, then there is no cycle, and if we are not able to visit, then there is a cycle. So we'll push it and we'll increment the count variable. And then we have done BFS while not queue is empty. We got the top element by q.print, and then we have traversed it to its neighbors. So what we have done first, we have incremented the integrity of that neighbor, and if we got any integrity as 0, we have pushed it into the queue, and if you are pushing it into the queue, we have to do count plus plus. That's it. And at the end, if we have count equal to number of nodes, then we say there is no cycle, and else we'll say there is a cycle. So that's how easily we have found it out, and you can check the explanation of a lot of the other folks. They'll directly teach you about topological sort and directly reverse engineer the problem. But we have figured out the solution from scratch.